Oh snap! I need to close this one. Go away.
Hey guys,
All right, so here's our objectives today. We've got a lot of stuff to cover, so let's just get to it. First, identify polynomial functions, recognize characteristics of the graphs of polynomial functions, determine end behaviors. I wish I had my camera for this one. Use factoring to find zeros, identify zeros, and their multiplicity. I think we talked about that a little bit, very vaguely, on one of the previous days. We're going to talk about the intermediate value theorem. Intermediate value is very, it's very hard theorem. Understand the relationship between degree and turning points. The last two, if we have time for those, we'll do those. But definitely we want to try to get through as much as through the first parts that we can. Okay. So we're good. Sure. Yeah, we'll I think they come back up, don't they? Yeah. So let's start here. I don't know if you can see that very well. No. That is the definition. Oh, no. Here is your definition of a polynomial. I think I've done that for you, haven't I?
Yeah.
So do we need to do it again? No. Right here. That is the definition. Okay? So let's move on. All right, graphs. So graphs of polynomials, they need to be smooth and continuous. I think I've thrown out those two words before, smooth and continuous. Definition of smooth and continuous might differ from professor to professor. When you get there, just do what they tell you, what they want. Okay? It was very annoying for me to go through college and not have those definitions match. But these are two things that we definitely can agree on. They have to be smooth and continuous. So when we're talking about smooth, well that's horrible. But you get the point, right? Smooth and continuous. Do I need to say more? No. Moving on then. And behaviors. So here's some nice things, some nice characteristics about polynomials that you can bank on. If you have even polynomials, then their end behaviors. See my hands? If they're even, they'll both do this bit. So you'll have one end that will go up into positive infinity, or it'll come from positive infinity, and it'll go back onto positive infinity as well. All even functions will do this. Okay? Unless they're negative, right, at the beginning. What happens if they're negative? You guys remember what happens when a is negative? Flips. But, so if they're negative, they'll just both go down in that direction. Make sense? But if you have an even polynomial, the end behaviors, they will go up, both of them, or they will go down towards negative infinity. Up if they're positive, down if they're negative. Cool beans? Now, the other thing that you can bank on is the odd functions, or the odd polynomials, I should say. If you guys remember a cube function, it does this, doesn't it? Yes. One comes down from negative infinity, and then it ends up going up towards positive infinity. They will also do that. So you'll have one behavior go up, while the other one's coming down. Now what happens in between just really depends on the degree of that polynomial. Okay? But end behaviors is what we're talking about. You can definitely count on this happening. Unless it's negative. If a is negative, what happens? It flips. So it's going to go, and then the arms will do that. Okay? So you'll have it, you'll have this red scenario where it's coming from positive infinity and they'll end up going down towards negative infinity. Okay? Questions on those end behaviors? Can I change a slide? Leading coefficient test. That's how they usually had you test what was going on. Because if you think about this, this will have a very big exponent, right? So the idea was if I put a big number in there, what infinity does it go to? Does it go to positive infinity or does it go to negative infinity? That was the idea, right? Big positive, big infinity, big negative, big infinity. Does that make sense? But we know how they behave, so we don't really got to do this test as much. But know that that's what it really is. All they're doing is plugging some number into the leading coefficient, see what infinity goes to, either positive or negative. But I know that if a is negative, they're going to be facing down, right? That whole business. Oh, that's what we just said. Notice, is this an odd? Is this first one odd or even polynomial? It's odd. What about the other one? Odd. What about this one? It's a negative even. Good. I was going to throw that in there. So they're very predictable. Wow, really? Yeah, they are. There's not very many options for n behaviors. For n behaviors. Okay? Questions on n behaviors. Ask me a question, please. Looking out there. N behaviors.
Okay.
Which of these two is negative?
Right.
The second one. It got flipped. Okay? This is so difficult. All right, cool. Using the leading coefficient test. Use the leading coefficient test to determine the n behaviors of the graph. With your hands, show me what's that going to look like. It's good! It's good. It's good.
Okay.
Both hands will do that. What happens in the middle, we don't know. But assuming, because there is some stuff here, like if it was just x to the fourth, then remember what I told you? It would just get a little flatter down here. You guys remember that?
Yeah.
But because there's some business going on, then it might have a little wiggle in there. Okay? Does that make sense?
Yes.
Cool beans. Moving on. Zeros. Those are all just the same. These are different names for the same thing. Okay? You'll get tired of hearing those. But whenever they ask for those, they're all the same. Zeros, roots, solutions. I don't like that they call them solutions because they're just x-intercepts. You think like you've solved it, which you have, but there's so much more to a polynomial and what solutions you can find. But that's what they'll be called regularly, interchangeably, by all your professors. Okay? Questions here? All right, moving on. Find all the zeros. Okay, so now we've got to go and find some zeros. That means that I want my equation to equal
0.
I want it to equal 0. Any ideas on how we can do this?
Factor.
Yeah, we can factor this. More specifically, because I do have 3, I'm going to factor by grouping. Cool?
Yeah.
I'm going to group those. I just wrote the first 2.
Can you let us try it on our own?
Sure. Not a bad idea. Go for it. I'll give you guys a couple minutes. Here's my toolkit here. 2 minutes. You know what? I'm going to do it over here too. You know why? Because I can. Just a heads up. How many solutions should I get?
3.
3. Why?
Well,
3 you will have.
because
Because you'll have a more
But
consistent.
degree is 3.
yeah, 3, but there will be repeats.
Yeah.
What if you don't get 3?
Then
Then
go
you
back
go
and check.
next up.
I got 2.
You should get
What's
3.
multiplicity, so it doesn't count as it counts as 3.
You want this thingy turned in?
Monday. Yeah, once you're done. Because I'm going to give you
Once we're
something
done?
else to do.
Once
you're
we're
done.
done with it, we turn it in?
Right.
No. Wait, save it for Monday because Monday I'm going to give you more to do
On that same problem?
on the same thing.
Neat.
Okay?
Should we just like kill this solution because it doesn't work? The same thing?
Time's up. Let's do this. Can I just, if you guys okay if I just go to the factorization of it?
Yeah.
The factored formula? I ended up with, correct me if I'm wrong, x plus 2, x minus 2, x plus 2.
Yeah.
Right?
Yeah.
Which means I can write it as x plus 2 squared, x minus 1, JK smiley face, lol. Right?
Yeah.
I can do that?
Yeah.
Go ahead.
Okay, so for the first two, whenever you factor, use the x to the third plus 2x.
You want me to see me factor it?
No,
Oh,
did you
using
take
the
out x
difference of
squared?
squares?
Yeah.
Oh.
What did you take out the x squared? What did the x squared minus 2?
I'll just show you what I did. Cool. So I split it there, right?
Right?
And the first part, I factored out x squared, which left me with x plus 2. On the second part, I factored out a negative 4, which left me with x plus 2. Oh, wait a minute. Okay, yeah. And then I factored out the x plus 2, which left me with x plus 2 minus 4.
X
squared.
And then this becomes two conjugates, x plus 2 and x minus 2. Okay? So hence, this is my factored form. So, why is that even useful? Can I erase this part right here, or are you getting it back? I can take it away? Take it away. Okay. So I wanna go here. And I want to
What the heck was that?
I was me trying to reach.
You look like a ballerina.
I am a ballerina.
That's weird.
Why is it weird? Have you not seen man ballerinas?
No.
Is there a problem with man ballerinas?
No, that's just
Who will carry the women ballerinas?
Carries a man balance.
Just don't put baby in the corner. Alright. So let me ask you some questions real quick. What does the end behavior on this thing look like? Can you show me with your hands? No Macarena. We're not voguing either, okay? Yeah, so we should have, because it's positive, it's going to go up that way, right? And over here it'll go down that direction. And what we just found, go ahead. Oh, I thought you had a question. So everyone's okay with the end behaviors for this thing? I found some zeros, didn't I? I found that there was a solution here at 2, and there's one here at negative 2, correct? Now, how does that help me? Because remember, here's what I got to have. It has to look something like this, doesn't it? Because it's a third degree polynomial, there should be at most 3 different slopes. And there are. Here's 1, 2, 3. Do you see it?
Yeah.
So, I'm going to draw something, and it might not work. But it looks like I've got to do something like this, right? Whoa. How do I get back up there?
It's in between those dots.
No, there's no more zeros. We found all of them. Those are it. There are only 2.
The third slope has to happen between the two zeros. Or the second slope.
It has to happen somewhere between the 2 zeros? So how do we draw this so that we hit our zeros and we still honor our end behavior?
It goes
The
through
dip.
arrows but curves down.
Put the
comes back
little
up
dip.
to the others.
-8.
A negative 8.
Zero.
Go down 8.
Oh, we have a y-intercept, don't we? 1, 2, 3, 4, 5, 6, 7, 8. So that means I've got to go up,
and then go down.
but I don't have a zero across. How am I going to do this and then come back?
Oh.
Oh!
Oh no, it curves, but it's like a.
So let's talk about this. I threw out some words yesterday. We talked about them today again. That word was, no, the word is duplicity, right?
Yeah.
Where do we have duplicity? At the negative 2, right? I'm going to change the color. We had duplicity at this point. If it's an odd function, well, actually it doesn't even matter if it's odd or even. But where you have duplicity, your function is going to bounce.
I remember you said that.
Your function is going to bounce.
So
So that means we're going to go up to that point,
And then
we're
it's
going to
gonna go
bounce down, then we can come get our 0, and then we can come back up.
Oh. Yeah.
Okay? Now, this part down here, I don't know. There are many scenarios. It can go like this, it can go like this, it can go like this, right? But I want to point out that where you have duplicity, your function will bounce.
Isn't there like case that like
Right now we've got pretty much most of it, don't we? So how do you guys feel about that? Not too bad?
Yeah, that's cool.
Questions on this slide? Duplicity, what does your function do?
Bounces.
Bounds.
Wait, so where is it?
Actually, I should say this.
At -2 because you have 2 of x positive.
Yeah.
So, but it's not going to go back.
No, it's just gonna.
Instead of going through it,
Hold on.
it's going to hit it and then bounce back off.
Yeah.
So you know how before it and then had it going through the point, now it's going to hit the point and then come back down. Oh.
Only because there's duplicity there. Go ahead.
I know why it bounces, like I don't physically see it.
Yeah, you're not gonna physically see it. It's gonna touch that point, and it's just gonna come right back down. So it'll become that point, but then it'll return. Now, it looks like a number what?
It just looks like a normal.
Exactly.
Yeah.
It's just the reasoning behind why it looks like that.
Right, because it's gonna bump and it's gonna come back down. Now, I said duplicity, but I should really be more specific. Whenever you have even binomials, they will bounce. Okay? And wherever you have odd binomials, it will cross through. Because duplicity just means you've got that solution happens more than once. Okay? Because I just want to be weird. Moving on? Alright, let's take a look here. So here we go. If r is a 0 of even multiplicity, then the graph touches the x, turns around. If r is a 0 with odd multiplicity, then the graph crosses the x-axis regardless. So, just like I said, if the binomial has an even degree, you're going to bounce. And if the binomial is odd, it's going to cross through. Okay? Swing batter. Let's move on. Finding zeros and their multiplicities. So, it's already in factored form, right? What are my zeros? And
How did you do that?
They're already factored out.
they're already factored. Right?
Yeah.
So there's where my zeros are at. Am I missing any?
Positive 5?
No.
It's right there. 5, 0.
Oh, I mean negative.
Okay? So, 1, 2, 3, 4, 5. And then here's -1/2. So I've got some solutions here, right?
Yeah.
What's going to happen at this guy right here?
It'll bounce.
Now, for starters, let me erase this so you guys can see the whole function. Show me your end behaviors. Show me your end behaviors for this one.
They left.
No.
Oh, it's -4.
I can't.
No, because the 4 should be.
Yeah.
Yeah, good job. Should do this. It's going to go from here to there, and it's going to come down here somewhere. Okay? Now, so, what degree is this polynomial?
3.
What degree is this polynomial?
5.
5. Good job. It's 5/5 degree. Now, at most, I should have how many slope changes? 5. Okay? What needs to happen here? Am I going to cross or am I going to bounce? I'm going to bounce. So it might bounce up to where? Wherever that y-intercept is at, right?
Yeah.
And then it might come around somewhere. And it might even do something like this to get those slope changes in there. See them? 1, 2, 3, 4, 5. Okay?
I want to graph this to really see what it looks like.
Yeah, you can graph it if you really want to see what it looks like. I just want to give you an idea of what it could be. Oops. I want that there. Questions on this slide?
Oh.
Can I change it?
Yes.
Oh, the intermediate value theorem. Guys, this is rocket science.
Is it?
So please listen. If f of a and f of b have opposite signs, one's positive, one's negative, right? So think about that. If I've got two outputs and they have opposite signs, what they're telling me is that there must be a solution between those two. Does that make sense?
No.
that real quick. If I have two outputs that have opposite signs, then there must be a solution between those two.
And
So let me show you.
intersection.
Yeah, well, let me show you. So let's say I have an x here, okay? So I'm looking at an x here. Do you guys want to make this output a positive or a negative?
Positive.
So that means it's going to be up here, right? So let's grab another x. We'll put its position over here. Now, if this one's positive, then my next output needs to be negative. So that means that between these two must exist a solution.
Zero.
It has to. Because how does it go from being a positive to being a negative?
It goes so far.
It has to cross
The x-axis.
the x-axis, doesn't it? And same is true if you flip them. If the first one was negative and the next one becomes positive, then there has to be some solution in between those two. Does that make sense? It makes sense when you see the picture, huh?
Yeah.
Otherwise, it's like, what are you talking about, English?
Wait. So is this like another way to find the zeros, basically?
No,
No, it's just telling you that they
this is just some axiom.
will
Okay.
eventually cross.
Okay. Like,
It's just an axiom saying, hey, you know what? If you've got two outputs with opposite signs, then between those must be some solution, right?
yeah.
This is so difficult.
It just sounds difficult.
When someone explains it. Yeah, when you read the axioms, the rules, the definitions,
It sounds difficult.
but they're written so that it applies to everything.
complicated when they word it?
Because they want to be smart.
I don't know. So, here's a question. Show that the polynomial has real zeros between -3 and -2. Is this a trick question?
No, this is just like its response to that, to show.
Look.
Yeah. I look.
No, show me mathematically. When they say show, they're saying show me mathematically.
Well,
Now,
why can't we just do like, well, when you see that 3 there, you see that it's positive, but you see
but
that
wait a
it's
minute.
negative.
but they're both negative.
Well, the thing is that when you plug it in there, it's gonna, because
give you a
the 10
different
is negative.
Absolutely. Did you guys hear that in the back? Tara, did you hear what she said?
No,
Okay, so this is how we're going to prove this. We're going to take those values for x, right? And we're going to plug them in and we're going to get the outputs. So if I put a -3 in here, that's going to give me 3 times -27 minus 10 times -3 plus 9. What?
What?
So it has to
That's
equal
negative
0.
81 and positive.
It should be 27.
I did.
That's negative 81. That doesn't make no sense.
Am I okay?
Yeah.
All right. I thought I made a mistake. So 3 times -27 is negative
81.
81. We're going to add 39 to that.
Explain.
Gives me negative what?
Explain what?
42? Yeah?
You're yelling at it while we're
Yes?
trying to explain.
Okay, so there's one. Let's do the other one. So we're going to plug in the 2. That's going to give me -8 minus 10 times -2 plus 9.
Oh.
I've got -24 plus 29. That's going to give me a positive 5. So I can see that these two outputs have opposite signs. Therefore, somewhere in between -3 and -2, somewhere in between -2 and -3, there should be some, oh, this was negative and then we had a positive. So there should be some 0 to get from there to there. And it has to be, who knows where it is, but it's in there somewhere.
I was talking about the Y's. The Y, if the Y was like opposite signs, then you got it. Right?
Correct. The Y's. The f of A, the f of B. Function notation. Be careful. Oh, good. I like that.
So A would be like X.
This is A. This would be f of A. This is B. That would be f of B. Cool?
Yeah.
Ask me questions? Gallus? Yahtzee?
So wait, so all you had to do
Gregorio?
was
Sonny
show
Rose?
that one was
Go ahead.
positive and one was negative.
What if it was what?
What if you get a Y that's a 0? Oh wait, that is the answer.
Then that would be a 0, wouldn't it?
Yeah.
You just answered yourself. I like that. That was good. You caught yourself.
Oh, so then, right. Yeah. So like if one of them has like A equal to
you should be able to find something there. Okay? Can we change this slide?
Wait.
Wait, 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 wait. Huh? Huh?
I asked my parents to help me do these questions just to get so they get mad. I did that to them yesterday. I was like, Mom, help me with this question. I know how to do it. It's really simple. She was like, I don't fucking understand it. She threw the pencil at the door, and I was like, chill. And she was like, what? And I was like, I already know how to do it.
My sister likes to watch me do my assignments for the week.
I got her mad, so she didn't.
I can change the slide now? Yeah?
Look at
Because
really
you're
mad.
checking your phone.
I got very slow last night.
Okay. Remember what I said about the degree and the number of slopes it should have?
Yes.
Well, stop and think about this. If I had, let's say, a third degree polynomial, those are all the slopes I can have, right?
Yeah.
But how many turning points do I have?
2.
Only 2, don't I?
Yeah.
Now, if I had a fourth degree polynomial, 1, 2, 3, 4, how many turning points do I have?
3.
3. You made the connection?
Yeah.
That's what this slide is about.
Wow. That's it.
It's going to have n minus 1 turning points,
Okay.
where n is the degree of the polynomial.
Okay.
Okay?
Oh, okay, so
So
if it's a fourth degree.
So if it's a fourth degree polynomial, how many turning points should I have?
3.
3. If it's a 10th degree polynomial,
Okay.
But if it's a fourth degree power. Oh, okay.
It's just 1, and then you have 2, and then you have 3.
questions on turning points, ask me a question. Go ahead.
I know it's supposed to be 3, but why do I see 4? 1, 2, 3, 4.
On which one?
That's just the.
Turning points. It turns here. There's 1, and it turns here from being negative to being positive, and then it turns here from being positive to be negative again. There's only 3 turning points.
That's just the amount of slope changes.
But there are 4 slopes, 4 different slopes. Maximum of 4 different slopes. Because you could have I guess that still counts, doesn't it? 1, 2, 3. Two turning points. And it doesn't have to turn from being positive to be negative.
It's just a turn.
It just turns. There's a turn in there, okay? We're good? What's up? Like, just stretching. I have the power. Are we good with end behaviors, people?
Yeah. Can we do it just for fun?
All right, show me end behavior for this one.
Wait.
Holy,
Oh yeah, it's 3. So
caught you off guard there, huh? What's the degree of the polynomial?
it's 3.
3. So they do this, right? Opposite ends. It's an odd.
You got the 2
Polynomial.
from the other.
It's odd.
Yeah.
Yeah.
Imaginary.
2,
It's this way.
3.
Wait, is it this way or this way? Wait, Lily.
It's in factored form, not in standard form.
Yeah, it's positive. Yeah.
So it should look like this.
But what makes it odd?
If it's
How many degrees for this guy?
2.
How many degrees for this guy?
1.
2 plus 1 makes the odd number 3.
3.
Oh. But it's not negative, right?
Yeah.
It's not negative.
Okay.
No. So that's why I didn't flip. So it's this and not this. Oh my god, I ran out of slides. We're done. Go ahead. No? Oh, my bad. Are there questions before I turn off the recording?
Uh-uh.
Going.